Okay, so welcome back, and we're going to answer some basic titration problems, usually involving the amounts of your titrant, amounts of your analyte. Okay, we're not doing the pH calculation yet. That's for another video. Anyway, so what we're going to do here is that we're going to solve for the endpoint volume, the concentrations, whatsoever. Okay, so let's have this problem number one. In a titration experiment, a student finds that 23.48 ml of sodium hydroxide solution are needed to neutralize 0.5468 of KHP. Molecular weight is given. What is the concentration of the sodium hydroxide solution in molarity? Okay, so the first thing you have to take note is that you have to identify which of the two substances is the analyte and which of them is the titrant. Okay, so I'll be giving you a tip. Okay, so the tip is usually the titrant are in solution form. Okay, so that means we have NaOH solution and grams of KHP. So which of the two is in the solution form? Of course, that is the sodium hydroxide solution. Okay, so this is our titrant. Okay, that means this one is our analyte. Okay, so after identifying which one is the titrant and which one is the analyte, we are going to write down their chemical reaction. Okay, so sodium hydroxide is a monobasic substance. That means it produces one hydroxide molecule. KHP here, this is a compressed term for potassium hydrogen phthalate. I don't know if I spelled it out correctly, but anyway, that is KHP, potassium hydrogen phthalate. This is used to standardize our sodium hydroxide solution. What we know about this is this molecule is a monoacidic or monoprotic substance. That means it dissociates to produce one hydrogen. Okay, so that means the reaction for KHP will be KHP producing H plus and Kp, anion. Okay, so for sodium hydroxide, that is sodium and hydroxide ions. So what we're going to do is that we are going to combine the two equation into a general chemical equation. So let me rewrite the whole equation. So what will happen in the two substances that we have is that sodium hydroxide will react with KHP to produce water and sodium potassium phthalate. Okay, so that is the idea. Okay, how come we were able to come up with water? Remember that sodium hydroxide produces sodium ion and hydroxide ion. KHP, on the other hand, produces hydronium ion and potassium phthalate ion. Okay, the hydrogen and the oxygen here combines to form water. Sodium combines with the negatively charged phthalate ion to produce this salt. Okay, so that's the general idea. Okay, so as you can see, the equation is balanced, and the stoichiometry is 1 to 1. Okay, so that means 1 mole of sodium hydroxide will react completely with 1 mole of potassium hydrogen phthalate. Okay, so this is our titrant, this is our analyte. Okay, so what we're going to do here is to establish the stoichiometric relationship of the two substances. We have 1 mole of titrant, and that is equivalent to 1 mole of analyte. Okay, so that's the idea. So that's the first step. The second step. First step, you have to establish the equation. Second step, you have to establish the uh, stoichiometric relationship. Okay, so the next thing you're going to do is to express the moles of your titrant and your analyte into equation that will give you the number of moles of your substances. Okay, so looking back at our titrant, this is a solution. Okay, so last time, if we have a solution, the formula to be used to get the number of moles of the solution would be the molarity of your titrant times the volume of your titrant in liters. Okay, so for the analyte, you can observe here that the analyte is expressed in grams. Okay, so to get the number of moles of your analyte, all you have to do is to obtain the grams of your analyte and divide it by the molar mass of your analyte. Okay, then what we're going to do. Okay, so according to the problem, we have to calculate for the concentration of sodium hydroxide. Okay, so looking at the equation, the concentration is this is the molarity of your titrant, or this is the molarity of your sodium hydroxide solution. So all we have to do is to cross multiply the volume term down. So we will get an equation MT equals grams of analyte divided by molar mass of your analyte times the volume of titrant in liters. Then we're going to substitute all the information that we have. So grams of analyte is 0.5468 grams. The molar mass of your analyte is 204.22 grams per mole times the volume of titrant in liters. Okay, so we have here a volume expressed in ml, milliliters. Okay, so if you want to convert that into liters, you're just going to divide that by 1000 and you will get a value of 0.02348 liter. So we're going to divide this by 1000 to get the equivalent amount in liters. Okay, so let's solve for that. Let me solve for that first. 0.548 2348. So the molarity of our titrant is 0.1140 mole per liter, or 0.1140 molar. Okay, so that's our final answer for the problem number 1. Okay, so it's very easy. Number 2. How many grams of KHP are needed to neutralize 18.64 ml of 0.1004 molar sodium hydroxide solution? So we still have KHP. We know that this is our analyte and this is our titrant. Okay, and looking back at our previous answer, we already established the relationship of titrant and analyte in terms of the number of moles. That is 1 mole titrant equal to 1 mole analyte. So let's say we were going to use the same equation for titrant as the molarity of titrant times the volume of titrant in liters being equal to grams of analyte divided by its molar mass. Okay, so we're asked what is the grams of our analyte. So that means we have to rewrite this equation. We have to cross multiply this on the other side. That would give us grams of analyte being equal to molarity of titrant times the volume of titrant in liters times the molar mass of your analyte. Then we're going to plug in all the given information. So this is 0.1004 mole per liter times we're going to convert 18.64 ml into liters. That will be 0.01864 liters times the molarity of our analyte, which is already given in the previous problem. That's 204 204.22 grams per mole. Okay, then we'll solve for the grams of our analyte. Allow me to solve for it. Okay, so the grams of the analyte is equivalent to 0.3822 grams. Okay, so that is our final answer. Okay, so let's try another problem. How many milliliters of a 0.610 molar sodium hydroxide solution are needed to neutralize 20 ml of a 0.245 molar sulfuric acid solution? Okay, which one is our titrant, which is our analyte? So this time they're both in the liquid form. Okay, so looking at this problem, we're going to add this into this. Okay, we're going to add sodium hydroxide into the sulfuric acid solution in order to neutralize it. So that will give us an idea that sodium hydroxide is our titrant, sulfuric acid is our analyte. Okay, so that's the idea. Okay, so if your problem tells you that you add this substance into the other substance, the substance being added to the other substance is the titrant. So in this case, that's sodium hydroxide. Okay, so anyway, so let's go and establish the equation. So sodium hydroxide is a monobasic substance. It will produce Na plus and OH minus. Sulfuric acid, on the other hand, this is a diprotic acid. Looking at the subscript of the hydrogen, that's 2. Okay, so that is a diprotic acid. So the first dissociation would be the dissociation of one hydrogen producing a bisulfate substance. Then what will happen next is that this bisulfate ion will dissociate further to produce hydrogen and the remaining sulfate ion. So the general reaction for the sulfuric acid will be H2SO4 producing 2 moles of hydronium ion and sulfate ion. Take note that the bisulfate ions are cancelled together. Okay. Then what do we have to take note? Okay, so what do we have to take note here? In order for the reaction to be completed, we should take note that if we have 2 moles of hydronium ion, that should react at exactly equal number of moles of hydroxide ions. So that means if we have 2 moles of this one, we should have 2 moles of this one. So that means we are going to multiply the equation for sodium hydroxide by a factor of 2. 2 sodium hydroxide, 2 sodium ion, and 2 hydroxide ion. And what will happen is that these substances, the hydronium ion and hydroxide ion, will form 2 moles of water. Okay, when we produce 2 moles of water, we can say that the reaction is complete. Okay, so that's a detailed process on how the reaction will take place. However, let us summarize what we have done. Okay, so in summary, it means we will have 2 moles of sodium hydroxide reacting with 1 mole of sulfuric acid to produce 2 moles of water and the remaining salt, that is sodium sulfate. Okay, so that's the idea. So this is our titrant, this is our analyte. Okay, so we can establish now the stoichiometric relationship of our titrant and analyte. So 2 moles of titrant is equivalent to 1 mole of your analyte. Okay, so looking at this equation, we have the titrant in solution form, the analyte in solution form. Okay, so in order for us to solve for the moles of our substances, we'll express that in molarity times the volume. So that is 2 times the molarity of our titrant times the volume of titrant in liters, okay, being equal to 1 mole of analyte. So that's molarity of analyte times the volume of analyte in liters. Okay, so looking back again at the problem, we are asked what is the, or how many ml of the titrant is needed. Okay, so we are asked to solve for the volume of titrant. Okay, so we're going to rearrange this equation. So we will get volume of titrant equal to molarity of analyte times the volume of analyte divided by 2 times the molarity of your titrant. Okay, by the way, we can now plug in all our information so we can solve for the volume of titrant. Okay, and so one tip for you: if you are asked to solve for the volume of your titrant or the volume of your analyte, you can opt not to convert the volume of the other volume in liters. Okay, so that's the idea. Okay, so the molarity of analyte is 0.245 molar times the volume of analyte. We have here 20 ml. So I'm not going to convert this in liters because we're not solving for the moles anyway. Divided by 2 times the molarity of our titrant, which is 0.610 molar. So you can see the molar units cancel out and the final unit is in ml. Okay, man, that's good. Anyway, so this is 2.45 times 20 divided by 2 times 0.610. The volume of titrant needed is, this is very small, 4.02 ml. Okay, so the volume of titrant needed to complete the reaction is 4.02 ml. Okay, so last one. How many milliliters of 1.28 molar sulfuric acid solution are needed to neutralize 60.2 ml of 0.427 molar potassium hydroxide solution? Okay, so this time we are going to add this into the potassium hydroxide, so sulfuric acid will be our titrant, potassium hydroxide will be our analyte. Okay, so the reaction is still the same. However, instead of having sodium as the cation for the base, we have potassium. And so we're going just to replace the sodium into potassium. But yeah, the reaction are basically the same. So that's sulfuric acid, 1 mole of sulfuric acid plus 2 moles of potassium hydroxide, producing 2 moles of water, 2 moles of water plus our salt, potassium sulfate. So we have here 1 mole titrant being equal to 2 moles of analyte. Also, our titrant and analytes are in solution form. That means to express their moles, we're going to do molarity times volume. Okay, so that is molarity of titrant times volume of titrant, 2 times molarity of analyte times the volume of analyte, and we're going to rearrange the equation in terms of the volume of the titrant, because we're asked the volume of the titrant, how many ml of the titrant. Okay, so that's Vt equals 2 times Ma times Va over Mt. Okay, so we're going to plug in all the information. So that's 2 times 0.427 molar times, okay, so I'm not going to convert the volume into liters, just as what we did in the previous answer, because we're going to express the final answer in ml. So I'm not going to convert this. divided by 1.28 molar. So the volume of titrant, that's 2 times 0.427 times 60.2 divided by 1.28. The volume of titrant needed is 40.16 ml. Okay, so the final unit is